Hello, welcome to this unit test or study guide on Unit 9, the behavior of gases. We're going to start off here talking about ideal gases. So the way this works, if you haven't seen one of these videos yet, the title up here kind of tells you where to go if you need more help with these particular questions. So if you struggle with these, you should head to the video on ideal gases, which will have the code 9.1 because this is Unit 9 and that's the first lesson. So to begin, the questions are, what is an ideal gas and under what conditions will a gas behave ideally? You should pause the video to answer the questions because I'm going to give you the answer in just 1 second. Ideal gases are kind of made up. They're not real. They are gases that we kind of think of when we think of gases, specifically because we don't want to have to do calculus to talk about gases. So we kind of put gases in this ideal situation so that we can do algebra instead of that calculus. So the ideal gas is going to have a situation where the particles are unable to interact with each other because they're very far apart from each other. And the conditions under which that will happen is very high temperature, so they're moving fast, and a very low pressure, so they're able to spread out. And we use the mnemonic device PLIGHT in order to help us remember that. The next question is, what are the postulates of the kinetic molecular theory? The kinetic molecular theory states that gas particles are always in motion, and their motion is described as random and straight lines. So they are moving constantly in random straight line motion. Next up, the gas particles are going to exchange energy when they collide with each other. So if we have a particle, let's say with 100 joules of energy and one with 50 joules of energy, and then they crash into each other, they will both leave that collision averaging out at 75. In that way, they don't lose any energy to the surroundings. They're just exchanging energy within, so there's no net loss of energy. Last up is that the volume of the particles individually is negligible. Because these particles are so far apart from each other, we just say that the volume of the container is the volume of the gas. In fact, the volume of that gas can change because gases are compressible. So if we were counting individual particles to get the volume, everything would be a lot more difficult. Because they spread and take up their entire container, this is a really fair way for us to measure volume. Postulate 4 tells us that gas particles do not attract each other, nor do they repel each other, so they are not having any intermolecular forces within the sample. And then finally, the average kinetic energy of the sample is directly proportional to the temperature of the gas. We spoke quite a bit about this when we talked about average kinetic energy the first time. Really what it means is that fast particles have higher temperatures and slow particles have lower temperatures. Kinetic energy, of course, is related to motion. So when we talk about atomic motion, really we're measuring it as temperature. Next up is the relationships of the properties of gases: pressure, temperature, and volume. Pressure and temperature have a direct relationship, so as one goes up, it means that the other would also be going up. The same is true for temperature and volume. If one goes up, then the other is also going to go up. They both go up, both go down. We also finally have the inverse relationship between volume and pressure. As the volume of a gas decreases, i.e. you squeeze it, all of those particles are going to feel that squeezing, so the pressure is going to increase. If you were to kind of expand the area that your gas can exist in and expand that volume, the pressure is going to drop because the gases are going to feel less of a squeezing on them, and they are going to crash into the walls of their container less often. Next set of questions is on the combined gas law. So the question is, what is the combined gas law? And then to convert 200 Celsius into Kelvin. The combined gas law connects the relationships of pressure, temperature, and volume. All three of those relationships that we had just mentioned fit into this equation. PV over T in the before situation will be equal to PV over T in the after situation. To go from Celsius to Kelvin is required for using the combined gas law because temperature's in the bottom, it's in the denominator. So 0 Celsius is a temperature that is allowed, but 0 Kelvin can never happen. So we convert all of our Celsius temperatures into Kelvin in order to use the combined gas law. To go from Celsius to Kelvin, all you have to do is add 273. So we would wind up with 473 Kelvin for 200 Celsius. Here we have a math problem. What is the temperature of a gas that begins at STP if the pressure increases and the volume also increases? If pressure and volume are both increasing, it only makes sense that temperature will as well. So what I like to do is take all of my data before plugging into my equation. So I have all of my information, P, T, and V, for before and after listed on the left side. And then I have plugged into the combined gas law right here. 1 atmosphere represents standard pressure. The volume of 2.5 liters is given here, and standard temperature 273. Makes perfect sense. My pressure is increasing from 1 to 2.5, and my volume is increasing from 2.5 to 5. So the question is just what happens to the temperature. Cross multiply and solve for T. Over here, you would divide both sides by that 2.5 to get T by itself, leaving us with T equals to 1,365 Kelvin. Next, we're up to the ideal gas law. What is the number of moles of hydrogen gas at STP in a 4.82 liter container? So we would take all that information, plug it into the ideal gas law, and we would wind up with 21 moles of hydrogen. Remember the ideal gas law, PV equals nRT. So P is pressure, V is volume, that must be atmospheres and liters. N is for number of moles, which is what we are solving for. R is the ideal gas constant, which will come in at 0.08206 liter atmospheres per mole Kelvin. And then finally, the temperature for standard temperature must be the 273 in Kelvin. Next up, define vapor pressure and describe what happens to vapor pressure when the temperature increases. I like to describe vapor pressure as the willingness of a substance to evaporate and become a gas. Some will say that it is the pressure on the surface of a liquid as it is evaporating to become a gas. It has to push against the atmosphere, and that pushing is the vapor pressure. So that'll be just fine. Some will also describe it as in a sealed container. It's the pressure of that gas that has already evaporated that's floating above the surface. So in a bottle of water, above the water level up to the lid, there will be water vapor, and whatever pressure is in that airspace, that would be the vapor pressure. But really what it boils down to, I guess that's kind of silly, it's the willingness of a substance to evaporate and become a gas. And as the temperature increases, that willingness will also increase. It is easier to boil stuff when the temperature is higher. Last topic is on gas stoichiometry. So we have this question. Aluminum and hydrogen monochloride, which you may know as hydrochloric acid, react in a single replacement reaction. What volume of hydrogen gas is formed from the reaction of 10.4 grams of the hydrogen monochloride? The first step of any stoichiometry problem is to determine your balanced equation. So here we have the equation, and now we're going to move forward with some calculations. Knowing that we have 10.4 grams of that hydrogen monochloride or hydrochloric acid, we have to take that and convert it into grams. So the 36.457 is the molar mass of HCl, which you could get just from adding H and Cl from the periodic table, or you could do my QMT charts. 10.4 grams of HCl comes out to 0.29 moles of HCl. Then what you need to do is a mole ratio to compare what you have to what you want. So that'll be this section over here. We have in our balance equation 6 moles of hydrochloric acid giving us 3 moles of hydrogen gas, but we're only working with 0.29 moles of hydrochloric acid. So X would represent the number of moles of hydrogen that we can get from this reaction. Solving for X, we get X is equal to 0.145 moles of hydrogen. In this case, because it didn't say, we're going to assume that we're at STP, but a really well-written question will give you the conditions under which this is happening. So we're going to take those 0.145 moles of hydrogen and plug them into the ideal gas law, solving for N to figure out the number of moles. Because remember, this is a gas, and the volume of this gas can fluctuate depending on the pressure and the temperature. So plugging into PV equals nRT, our final number of moles, the final volume for hydrogen is 3.25 liters. That's it. That's everything. So if there are any questions, leave them in the comment section below the video. I would go back and look at some videos of things that were a little perplexing to you, maybe hear them a second time. Subscribe so you don't miss our next unit. It'll be on solutions. I can't wait to see you there. Bye.